Hello, everyone. I'm Glen MacDonald, professor of geography here at UCLA, and I want to welcome you to the Ursus Symposium on heat domes, atmospheric rivers, bomb cyclones, and climate whiplash, California's climate and weather now and in the future. I'll start by apologizing. We had some technical issues at UCLA. Some of you might be coming in a bit late. I am really sorry about that. The IT people have been working furiously to fix it. We will record this, so it will be available recorded. And if you know people who couldn't make it on because of technical issues, please let them know that we will be recording it, and we will be sending out a link to everybody who registered so that you can watch the recorded version. The Ursus Symposia are a group of public symposia. They're meant to engage and communicate with the public about issues of environment and sustainability in California and the wider West. They are part of the Endowed Chair of Geography of California in the West at UCLA. We thank Hollis Lenderking for very generously endowing this chair and bringing these public symposia as one of the activities of the Endowed Chair. We've had symposia on the history and impact of John Muir, on urban conservation, the Ballona wetlands, and today on weather and climate. Stay tuned because there will be further symposia in the future about California in the West and our environmental issues and sustainability. And I would like to then start by having a brief introduction of where we are. And so, folks, let's talk about the weather. How can you avoid talking about the weather, particularly right now? You turn on your television, you pick up, you look at your favorite blogs, you pick up reading material, and you see all about what's going on with the wild weather in California. And it isn't just this year, but it's been back. 2022, parched California set a record for the three driest years ever recorded. In fact, some research shows that the dry period that we experienced up to the 2021, end of 2021, was the driest prolonged period in over 1,200 years. And then boom, the winter of 2022-23 comes along, and we have record snowfall in the Sierras. We see that we had at Mammoth Lakes over 700 inches, up at the Palisades in Tahoe, another 700 inches of precipitation. Just incredible. And then we come into this summer, and we are smashing daily heat records all over the state. Just in this past couple of days, we've had daily heat records broken in Lancaster, 103 degrees, Palmdale, 104, Paso Robles, 107, Woodland Hills, 113, San Jose, 100, San Rafael, 105 degrees. Breaking daily heat records one after the other. We will break a bunch more today for sure. As you all know, it is super hot out there. Now, the implications of these wild weather that we're having go beyond being uncomfortable or having to change your day or maybe plan a beach day when you were going to do a hike instead. They have grave implications for California's sustainability and resources. If we take a look then at that drought, if we take a look at 2021, the picture of Lake Oroville, second largest reservoir in California. During the heart of that drought, Lake Oroville was down to a bit over 20% of its capacity, between 23 and 28% of its capacity. Hydroelectric generation from Lake Oroville basically had to shut down for long periods of time. Water transfers from the state water project to some of the districts in Southern California was basically cut to zero, and we had severe water rationing in some of these districts. Then we move on to 2023. We have Lake Tulare, which was a lake that basically disappeared as it was kind of drained for agriculture and things like that, reappears in the southern San Joaquin River Valley. We have a situation where we had over 90,000 acres of farmland and orchard land inundated by the re-emergent Lake Tulare being fed by all the precipitation that we saw, adding that snow to Mammoth and to Lake Tahoe. Then we go into this year. Anyone in Southern California knows that we are suffering under the airport fire, the line fire, and the bridge fire, all relatively large destructive fires. The state just this week now has hit 1 million acres of area burned this fire season. And we're not done yet, folks. We're definitely not done yet, particularly in Southern California. And the high temperatures that we've been having have exacerbated this fire risk. So this is more than just talking about the weather. It's more than whether you should put on shorts or long pants. This has big implications for the state. But this is not California's first rodeo on the kind of wild weather ride. We have had in the historical period, and we know from geologic evidence and other evidence in the prehistoric period, some pretty wild weather in the past. 1862, we had weeks of high precipitation, then followed by a warm storm and lots of snowmelt in the Sierra Nevada. We essentially filled the Central Valley of California like a bathtub. Here's a picture of downtown Sacramento during the Great Flood of 1862. That had huge economic costs, aside from loss of structures and lives, many, many cattle killed. And this was a huge, huge, big natural catastrophe in the early days of the state. And then talk about whiplash. You move down into the period between late 1862 and about 1864, 1865, we have very high temperatures and a mega drought. And here's a picture of a dying orchard at Mission San Luis Rey. There's a quote, "Thousands and thousands of cattle have died and are dying. And those that are left stalk about like specters." This was the great drought. It literally changed the social and economic fabric of the state, because many of the Mexican rancheros and the pastoral economy that had developed under the Spanish and Mexican authorities was basically removed or eradicated because of the huge economic losses, loss of cattle, loss of orchards, and things like that. It changed our state. Moving up into the 20th century, we still see the impacts of these sort of extreme weather events. This is a Los Angeles Times article on a large, what they call the New Year's Eve or the New Year's flood, which hit the Los Angeles area, Southern California, in 1934. And this was very, very important: destruction of property, loss of life. And Woody Guthrie, the famous American folk singer, he wrote a song about it. And I give a quote from the song right there, Los Angeles New Year's Flood. Woody Guthrie was interviewed and talks about that flood, and then he sings his song. It's available from the Smithsonian. I'm giving you a YouTube link there. I invite you to go listen to it as he talks about the water coming down from the mountains, the impact of the flood, and then he sings a really interesting and good song about it. So this not only like affected Los Angeles, it affected popular culture. Following quickly on to that, we have a double whammy, The 1930s in the United States was one of the hottest decades on record. 1938, in terms of the historical records, was the hottest year for California. But the early part of 1938 was a year where we had massive flooding in downtown Los Angeles. And at this point, after floods in the 20s, the early 30s, 1938, this led to a really, really, really strong push then to complete channelization or to channelize the rivers and water courses in the Los Angeles area. The Los Angeles River that you see as a sort of a concrete culvert, this is a legacy from this time period where these large destructive floods came through the Los Angeles area. But then what do we see as we move into the autumn of 1938? 1938, as I mentioned, was the hottest year on record up to that time period. And we have high temperatures and devastating fires, much like today. Fires were burning in Pacific Palisades, were burning in Topanga and in the Lake Arrowhead region, and destroyed then completely a very large and famous sort of resort up there, Arrowhead Springs, burned it completely to the ground. If there's a strong sense of deja vu there, there should be. Those fires occurred in November of 1938. And as I said, we probably still have things ahead. So wild weather and things like this has been something that have been with us for as long as the state has existed. But what's different about today? What else might we think about today? Well, we have to think about anthropogenic climate change and the influence that we are having on the global climate system. I'm presenting here a graph which shows California average temperature and then atmospheric CO2 concentrations in parts per million by volume. Temperatures are in degrees Fahrenheit and the concentrations on parts per million by volume. And what you can see from 1895 to the present day, and this goes to 2023, you have a significant upward trend in temperatures in the state of California. And that really begins to steepen about 1980 or so. About the same time, you see that we've had an increased amount of CO2, atmospheric CO2, greenhouse gases from human activity. And that begins to steepen at the same time California's temperatures begin to steepen, late 70s, early 1980. There's no question about it. Climate models, empirical evidence, analysis shows that there is a relationship between these increasing greenhouse gases and increasing temperatures, not just in California, but globally. I want to point out something else here. There is the 1938 peak warming that we had. It has totally been eclipsed as we move into the 21st century. We've had many years which have absolutely eclipsed that peak warming, and they are concentrated, as I said, in the 21st century. So yes, we've had wild weather in the past, we've had drought, we've had floods, we've had huge snowfall events, we've had prolonged and significant heat spells, but we have a new playing field, and that playing field is changing as increased greenhouse gases occur. We're changing all sorts of things about the atmosphere, including the temperature. Now, when we look at and we listen to the news and we read, we hear all kinds of terms: heat dome, atmospheric river, bomb cyclone, climate whiplash. And we might wonder, what does this all mean? We might wonder, what is causing the weather that we're seeing, particularly in the last few years? And where are we headed in terms of weather in the rest of the 21st century as these greenhouse gases increase and California faces the prospect of even greater changes in climate? Well, today we've brought together three preeminent climate scientists from the state of California to help you understand that and to answer some of your questions about this. First of all, we have Daniel Swain of UCLA Institute of the Environment and Sustainability. Daniel is a climate researcher, but he's also a climate communicator. Daniel has, if you pick up the LA Times, you look at the national news, you will see Daniel Swain quoted. Many of the terms that I just threw out, climate whiplash and things like that, Daniel has introduced into the popular press. He has introduced those terms and he can explain them and how they relate to what's going on with the climate today. He has a Weather in the West blog. I invite you to look at it. It's used by the media. It's a really important source of information on this. He is an epic science communicator. Then we have talking about where we're going in the future. We have Park Williams from the Department of Geography at UCLA. Park Williams is a time traveler in climate. He deals with what's going on today, but he also looks into the past and looks at how climate changed in the past and what caused it to change over hundreds to thousands of years in the past. And he works a lot on where climate is going in the future. But not just climate. He looks at things like drought, water resources, and fire. And he is going to give us his unique perspective of where we're headed in the 21st century. For his work, Park was a 2023 winner of a MacArthur Genius Award. And finally, what is our state going to do about the challenges that we have with weather today and anticipating and planning for the challenges of climate change? This is where the rubber hits the road for California sustainability. And we are very fortunate to have the person here who is in charge of that, who has to kind of marshal all that information and help then advise the policymakers in our state at the highest level about the weather today and about where the climate is going in the future and what this all means. And that is California State Climatologist Michael Anderson. So you are really getting it from the best, the most knowledgeable people. We're glad that you've joined us. And now I would like to turn this over to Daniel Swain.
Well, thank you for that introduction, Glenn. And I'm very impressed to see how many folks are still joining us live despite the technical difficulties. A testament to the level of interest in this topic, I think. Just bear with me for a moment while I share my screen, and then we will be off to the races. All right, everybody. So what I was tasked with talking about today, and hopefully this will serve as a lead up for what other folks are going to talk about in the other two presentations, is where we are today in terms of how the climate and therefore how the weather in California has already changed in a warming climate. Because I think we're living in this moment where a lot of things that were just a couple of decades ago, still predictions about a plausible future, have essentially come to pass, and we're now living in that present. So there's the question of sort of how has that evolved, and also what does that mean for what might be coming next in terms of which predictions essentially came true quite directly, and which ones might still be a little bit uncertain. So a very brief primer on global warming overall, and I'll make it very brief given Glenn's introduction and the time we've got. But, I really just wanted to show a spatial map of change. And this is a map that's valid up through last year. If you include the 2024 data, it looks ever so slightly more red and orange than this map does, because this year was at least as warm as last year in many parts of the world, some cases warmer. But we know, of course, that the Earth on average is warming. But I think the key part here in linking climate change to changes in weather is that global mean temperature is essentially a heuristic. It is a very important number, but it is a number that in itself does not necessarily tell us a lot about what's happening on the ground in any particular place at any particular time. No human on Earth, no tree, no animal individual has ever experienced the global mean temperature. It is a very useful but still statistical construct. Uh, and there's a few key things I think that are important to recall, which is that the modern warming we're seeing is being caused by the accumulation of heat trapping greenhouse gases in the Earth's atmosphere that's almost entirely caused by human activities, not just fossil fuel burning, although that is the number one reason, but even things like the way we've changed the use of the land on Earth, and agriculture and land use changes as well are also a significant contributor. And the other piece here to note is that the warming level is not the same everywhere. There's a few general patterns that I think pop out from the map above, which is that the warming is faster over land than oceans. That's true essentially everywhere. And also the fact that the Arctic is warming faster than anywhere else in the world. So when we hear about that global mean number, if you happen to live on land, as most humans do, your actual local rate of warming is quite likely to be a lot faster than that global average. And that's true too when we talk about these nice round number global temperature targets. So where are we now? Well, the Earth has warmed, depending on the averaging period you use, probably about 1.3 degrees centigrade in terms of the multi-year average, although the last 2 years have been fully 1.5 centigrade or so above the pre-industrial average. So there has been a recent little spike in that warming, even though that multi-year average is still a little below 1.5. But we're getting closer and closer to that 1.5 degree value, and we're on a path toward And I'm giving a wide range here because there's still a lot of uncertainty, somewhere between 2 and 3 centigrade, or about 2.6 to 5.4 degrees Fahrenheit of global mean warming. And that range is partly a function of uncertainty about how the Earth will respond to the further emission of greenhouse gases, but it is even more a question over how much more of those greenhouse gases we're actually going to emit into the atmosphere. And that remains a big question that is not solely in the domain of physical science, but is a policy question. So it is directly related to the politics and economics of the world we live in. I won't be talking about any more of that part of it today, but I do think that's important perspective for the conversation we're having. So, and this is something that Glenn already alluded to. This data is now updated. I updated this a couple days ago. This is correct up through this most recent summer. So there is summer 2024 on this graph of summer maximum temperatures when you do the cookie cutter average for all of California. And so it's pretty clear, of course, that summers are already hotter than they used to be in California, and that the two hottest summers on record have occurred in the last 3 years in California. And so the rate of summertime warming in particular has been especially pronounced since the 1980s in California. So the rate of warming has accelerated in recent decades, which is what you would expect from the global climate forcings during that period. We are seeing faster warming even within California in some places versus others, faster warming in many cases in inland areas. That's a prediction consistent with climate models. Recently, seeing some faster warming at higher elevations too, which has major implications for snowpack. We might hear a little bit about that later. And as I mentioned, this past summer was tied with 2022 for the hottest summer, effectively statistically tied for the state of California. It was the singularly hottest summer on record for other Western states, though. Notably, if you're joining us from the LA County or some of the other coastal sections of the most populated counties in Southern California, this past summer was not the hottest summer on record, and you may have noticed that conspicuous dissonance between the west side of LA, for example, and even the east side of the county. So if you go to Palmdale, an extraordinarily hot summer and a very hot place to begin with, not so much in Santa Monica. And so there is this interesting contrast where the very hottest summers on record across most of the land area of California in recent years have not necessarily been the hottest periods on record, where a lot of people, perhaps even a majority of California's population, lives close to the coast, especially in Southern California. And the reason for this, and this is language you may have heard, is that we are seeing heat waves that are longer lasting, occurring over a wider season. And yes, they are also more intense. We have, even this summer in the last few months, hit all-time high temperature records in some places as recently as yesterday in some places in Southern California, at least for the month of October. Looks like, as Glenn mentioned, this afternoon may set some new all-time monthly October records across a wide swath of the Southwest. But it's not just a question of temperature, of course. We've been talking about the hydroclimate, and right now this is really in the news with the ongoing catastrophe in the Southern Appalachians as a result of the hugely historically significant flood event in the wake of Hurricane Helene. I think that there is renewed interest in this broad sort of overarching idea behind hydroclimate change in a warming climate. And with that, I want to introduce yet another new term, which is the expanding atmospheric sponge effect. And the way that it works is you can essentially envision that the atmosphere in many ways acts like a progressively larger ordinary kitchen sponge in a warming climate. And that sponge has the ability both to soak up water that you might spill on the counter, and also it can yield water if you wring it out over the sink or something. You can imagine if you have an ordinary sponge and then a comically oversized sponge. And by the way, this is actually possible. You can replicate this using comically large sponges, which apparently can be found in certain novelty stores. The larger sponge can both evaporate more water if it's empty, if it's dry, so you can absorb a much bigger spill. And if it is saturated, it's going to yield a lot more water. So what this means in the analogy is that a warmer atmosphere has both a higher capacity to evaporate water when there is water to evaporate, but also a higher ceiling on the most extreme precipitation that it can produce. And this explains a lot of what's going on when we think about changes in drought and flood and wildfire risk in a warming climate. So, in other words, the atmosphere becomes thirstier on average when it's not raining, but also capable of much heavier downpours when conditions are right for precipitation. And if you look at the precipitation only perspective on this, and this is from work we've done, 2018 now feels like a long time ago, but I think the general implications still hold up. We don't really know on average if the average annual precipitation in California will increase or decrease in a warming climate. There's a chance that it might increase a little bit in Northern California, more likely, and maybe decrease a little bit in Southern California, but that's not a very strong prediction. Still, even today, even 6, 7 years after this paper came out, but those very same climate models that suggest that we have uncertainty in how California's average precipitation might change agree pretty strongly that the variability between wet and dry conditions, low and high precipitation, will increase in a warming climate. And that is pretty interesting because this comes more from the wet side than the dry side, by the way. So there's more evidence that extremely wet events, extremely wet years, extremely large individual storms will increase, but there is also some, albeit weaker, evidence that the very dry years may become more common, but most of that's driven by the wet side. But the point is, if you add those two things together, there's quite high confidence that what we call precipitation whiplash will increase in a warming climate. And this is particularly pronounced in Central and Southern California. So this really is something that's going to affect LA and the rest of the Southland pretty directly, we think. If we look at the broader view in the Southwest, although these plots actually look pretty similar just for California, you can see in the long run, there's been a trend towards more frequent and severe droughts pretty unequivocally when you look at the whole picture in the Southwest, and that temperatures are unequivocally a lot warmer than they used to be. But what's curious is that there hasn't been a corresponding enormous decrease in precipitation over the same period. And yet there is a robust increase in drought frequency and severity when you take into account all of the factors that can relate to drought, so both precipitation and evaporation. How does that work out? And the answer is that essentially the same amount of rain and snow just doesn't go as far as it used to because there is more precipitation occurring, but potentially on fewer days. And we do expect this increased intensity of precipitation to occur even if we end up seeing fewer storms overall. We clearly have less snowpack already than we used to, and stronger evaporative demand. You can blame that expanding atmospheric sponge for that one. And another piece of this is that all the droughts we used to have in California and the Southwest, and really all over the world, they might have been associated with warmer or cooler than average temperatures. But now, effectively, in historical context, all droughts are hot droughts because relative to the historical baseline, it's almost always warmer than that historical average. So this has implications, of course, for wildfire, as you might expect. And we've already found that the frequency of extreme fire weather conditions, so not necessarily telling us directly about the fires themselves, but about the atmospheric conditions and the vegetation moisture conditions that are favorable for extreme fire behavior and very rapidly spreading intense fires, has essentially doubled, more than doubled, actually, since the 1980s already. That's a strikingly large increase in a period where the long-term precipitation has not necessarily decreased greatly in the same region. So this is really coming from drier vegetation. So what we're seeing is that this increasingly large atmospheric sponge is more and more easily extracting water from that landscape, both from vegetation and more importantly from the soil that would supply that vegetation with moisture during the dry season. And that has led to larger and faster moving and more intense wildfires. And so, of course, this is not the only reason why we're seeing an escalating wildfire crisis in California. In 15 minutes, I probably don't have time to talk about the details there. But just suffice it to say, this is a big part of what's going on. Oh, there we go. And on the other side of this, the flip side of that expanding atmospheric sponge is the wet side, of course. And where does California get most of its moisture? Well, most parts of the state, with a couple of exceptions, in the deserts and in the high mountains, it's wintertime atmospheric river storms. You may have heard about these kinds of events. It's kind of an evocative term, but I think it's a pretty appropriate one because when you look down on these features from Earth orbiting satellites, they really do look like rivers in the sky. And they are composed of these filamentary, these narrow but concentrated corridors of water vapor moving quickly over your head. So the technical quantity plotted here is the integrated vapor transport. But what you really, the way I like to think about it is, these rivers of moisture being pushed by sometimes hurricane force winds in the air above your head. So it's lots of water in vapor form moving quickly over your head. And they don't necessarily produce a whole lot of precipitation over the ocean all the time, but when they hit California's coastal mountains or the Sierra Nevada, when that air is forced upward, cools and condenses, all of that water can fall out in a hurry in the form of really extreme precipitation. And in a warming climate, as that ceiling on how much water vapor the atmosphere can hold increases by around 7% per degree centigrade or 3 or 4% per degree Fahrenheit, the ceiling on how intense these atmospheric rivers can become increases to the point that we will probably eventually start to see atmospheric rivers of unprecedented intensity. And this is just the summary graphic from a fairly extensive study on this, but the basic idea is that it's quite likely that the likelihood of very severe multi-week sequences of intense atmospheric river events has already increased in California, perhaps even doubled, but it's done so largely quietly in the background. So the degree to which we think the warming we've already seen has increased the risk of intense to unprecedented atmospheric river sequences is perhaps more than we've actually yet experienced. And this leads to an interesting question about whether recent trends are fully indicative of the future that we're likely to see in California. We've been so focused on drought and wildfire that we may have neglected to think as much about the risk of a catastrophic flood. And so, why do we care about this? Well, I think for some folks, it's probably pretty obvious, but just a few specific examples. This episode in Southern California back in late 2017, early 2018, when we had what was then the largest wildfire in modern history in California in December 2017, the Thomas Fire, which immediately transitioned to one of the most devastating debris flows on record in Santa Barbara County shortly thereafter when extremely heavy rain fell on this burn area. And yet, if we average the climate or the weather over this 2-month period, you would have said that it was mostly sunny and breezy most of the time with below average precipitation. So what I wanted to illustrate here is if we only consider changes in average climate, then we're often going to miss the point for the most consequential events. And just a couple of other examples from other parts of the state here. For this from Northern California, and I've been using some variation on this slide now for years, and every couple years I just add a new image from DWR because, I mean, it is just kind of amazing. This year we could have added a 2024 image of the slopes of Oroville Dam itself on fire earlier this year. But suffice it to say, we are seeing, at least anecdotally, that recent experience, it isn't just drought and wildfire. If you actually look more closely, you can find examples where we've been extremely wet or even record wet in some cases in different parts of California in the same decade that we've also been record dry and seen record-breaking wildfires and record-breaking heat. And this is a slide I created for another presentation in San Bernardino County just a couple of weeks ago. But I mean, another county that's really just been really at the epicenter of, I think, climate impacts over the past decade. Some of these are, ongoing. I mean, the line fire, that photo was taken a month ago, and that fire is still burning, and there are still evacuations in effect for that event from the slide created a month ago, which is kind of remarkable in its own right. So I think all this is a bit of a grand challenge to sort of transition into the next conversation, not only for policymakers and decision makers, but really for anybody who sort of inhabits this space in different sectors in California, people who put science to policy, but also policy to implementation. So the physical reality we expect, just to summarize, an increase in both precipitation intensity, but also in overall aridity, thank that expanding atmospheric sponge, with a fairly dramatic loss of snowpack, honestly, though we will still see major snow events in the mountains occasionally, at least, with, of course, more extreme heat and more intense runoff. We've seen both of those just this past year. And so the question really becomes, can we mitigate some of these things simultaneously? Not only flood, not only drought, but both along a spectrum that is not unfamiliar to California, a land of extremes for really since time immemorial in a certain sense, but an even greater magnitude and frequency of those swings is likely what we are beginning to experience now and really should be thinking about how we need to mitigate. And the same thing is true with wildfires too, because there's an escalating problem there, but wildfires too are a part of the natural landscape and the natural history of California. So, in a certain sense, there's nothing new under the sun, but in another sense, what we're seeing now is very different than the conditions under which California developed over the 19th and 20th centuries. So it's becoming clear that historical paradigms and management practices aren't going to cut it in the 21st century. And I think what we do need are flexible and proactive interventions and adaptations that are going to be needed, that are commensurate not just with sort of change in one direction, but in some cases, changes in multiple directions at once, which I think is challenging. But if we prepare in that way that's appropriate for those whiplash changes, we'll be in much better shape than if we had focused only on flood or only on drought on its own. So with that, hopefully we'll have some time for questions at the end of all three presentations. Thank you.
Okay. Thank you, Daniel, for a nice setup. 1 second. Okay, so that was great. Now I've been tasked to speak about the future of climate in California, and I think it makes the most sense in thinking about how we can predict the future of climate anywhere, to think a bit about the past. And the reason is because it's really because of the evidence all over Earth's landscape and on the ocean floor of dramatic swings in Earth's past climates that we really feel that we know that the current experiment that we're running with putting carbon dioxide in the atmosphere at an unprecedented pace is going to have a dramatic effect on the future climate. Anywhere you look on the landscape of the globe, you can see evidence of past climate changes, and people have undoubtedly been noticing these for hundreds or thousands of years. On plains far away from mountains, we find gigantic boulders. People for hundreds or thousands of years would have concluded that the only way those boulders could have gotten there is from giant ice sheets. There's evidence of massive swings in climate at a global scale and regional scale almost everywhere. In the Western United States, we see great evidence that the hydroclimate, that is the way that climate interacts with water, is extremely sensitive to global climate changes. About 6,000 to 9,000 years ago, the Earth's tilt was slightly different than it is today. The Northern Hemisphere was getting more sunlight during summertime. The atmosphere's circulation was affected as a result, and the Western United States was much drier about 6,000 years ago than it is today. In the Sierra Nevada, there's evidence in lakes that lake levels throughout the Sierra Nevada were much lower than they are today. Here we're just looking at a fascinating picture of archaeological evidence of human habitation in an area that is now about 60 meters or 60 feet or 20 meters deep in Lake Tahoe. And so this site here with these bedrock mortars where the people used to grind food products, this would have been a site that was obviously above water on the shore of Lake Tahoe, near the shore, for a long period of time. And now, for recorded history, this area has remained underneath water. And so right now, by putting carbon dioxide into the atmosphere at an unprecedented pace, we are clearly conducting a global atmospheric chemistry and climate experiment. In the 1800s, scientists began hypothesizing that the burning of coal would be leading to carbon dioxide accumulation in the atmosphere, and that this could have catastrophic effects on global climate. Here we're looking at a record of carbon dioxide in the atmosphere going back for 800,000 years, preserved by ice cores. And then that record is appended with the modern observational record at the very end. And what you can see is that here in 2024, we are dramatically off the scale of what we would call natural climate variability. This is because we are putting carbon dioxide in the atmosphere far faster than the Earth's environment is able to pull carbon dioxide out of the atmosphere. And this carbon dioxide, I think it's important to remind everybody, it actually weighs something. It's not just some gas that goes away and miraculously causes warming. It's actual mass they're putting in the atmosphere. We're treating the atmosphere essentially like a garbage dump. Carbon dioxide is a byproduct of our energy production. And these days, globally, we're putting about 40 billion metric tons per year of carbon dioxide in the atmosphere. This converts to 88 trillion pounds of carbon dioxide to be put in the atmosphere. In the United States, we're responsible for about 1/9 of this, and it comes out to about 33,000 pounds of carbon dioxide for each of us here in the United States. That's averaged across, that's our country's emissions averaged across 333 million people. And to put this into terms that at least I can understand, this is kind of the equivalent of if every group of 80 people in the United States was to chop down a tree the size of General Sherman each year and turn that tree into gas and put it into the atmosphere. It's just a remarkable amount of carbon dioxide that we're emitting into the atmosphere. And so this is a really extreme experiment that we're running. And in the mid-1900s, scientists began using computer models. They're trying to create computer models to understand the effect or the results of this experiment. Ideally, we would be able to use these computer models to perform experiments to see what will happen in the future if we do this or do that. Experiments that may be too dangerous to carry out in the real world can at least first be carried out into a computer. But this art of computer simulation, climate, has evolved a lot over the last 70 years or so. And the first global climate models in the 1960s were just two-dimensional models that just pretended that a two-dimensional Earth was covered partly by sea and partly by land. And scientists used that to those early models to try and understand how the globe's climate could change. But these models couldn't give us any information on the future climate in a region as small as California. By the 1980s, we at least had kind of realistic continents in the global climate models, but still, as you can see, squinting in at California really would have been basically fortune telling to try and tell anybody what the climate of California would be like as we continue on with our global CO2 experiment. These days, climate models are quite a bit better, but still limited in detail. Last decade, the average climate model had a spatial resolution of about 200 kilometers. That is, each pixel in a climate's model, where everything is kind of spatially homogeneous within, was about 200 kilometers by 200 kilometers. So California was represented by, say, 6 or so grid cells across, or 6 or so grid cells. This decade, things have improved dramatically. Now we're up to, say, 36 grid cells or so across California. Importantly, in the Western United States, topography is really complex. The Sierra Nevada and the Coast Ranges of California have huge influences on the way that water vapor moves and condenses across California. And so if a climate model has a simplified representation of topography, which it must if it has a low spatial resolution, then it is also going to have a simplified and potentially not trustworthy impression of the climate of the Western United States, and especially in California. But in the last decade or so, there have been some really exciting, remarkable advances that I'm going to draw on for the rest of this talk. And these advances have been made in the field of what we call dynamical downscaling, where scientists have taken climate model simulations and fed them into much more complex, high-resolution regional weather models, like the weather models that produce our 10 or 20-day forecasts in the Western United States. We, of course, can't forecast what the weather is going to be like on a given day 50 years from now. But these weather models, if they are informed by the climate model about how the globe's climate is likely to change, these weather models can then simulate how the global climate changes should manifest at much finer scales, like the scales in California. And so here in this pair of maps on the right, I'm just showing you what global climate models say should happen on average to spring precipitation in the Western United States. And so you can see it looks very cartoony, not much spatial detail at all. And then those same global climate models, when their simulations are fed into a regional climate model and the downscaling occurs, then we see something with much higher spatial resolution, much more interesting detail. And so it's these simulations from the regional weather models forced by global climate projections that I'm going to be talking about for the rest of this talk. I'm going to be drawing on a new data set produced by Stefan Rahimi and Alex Hall and others at UCLA a couple of years ago now. And importantly, we don't, one of the biggest uncertainties about how climate is going to change in the future is human behavior. We don't know how humans are going to behave. Maybe we'll burn every last bit of coal that we can get our hands on, or maybe we will dramatically curb greenhouse gas emissions. In this talk, I'm going to be showing projections, assuming one single future climate or future emission scenario. This assumes that we continue to burn greenhouse gases at an increasing rate through the rest of the century. It's not what is thought of commonly as the worst case scenario, but it's still a pretty bad scenario. And so what I'm going to be showing you is hopefully a future that global society will choose to avoid by reducing carbon dioxide emissions. And so how is California's climate projected to change in the future? We'll start with the simplest variable first, temperature. As the globe's temperature changes, California's temperature is expected to rise as well. Here on the left, I'm showing a smooth record showing the average and range of simulations from 14 different climate models. And they suggest that in the next couple of decades, if we can compare the average temperature of the next couple of decades to the average temperature of the 1980s and 90s, these climate models project that on average, California will be about 3.5 degrees warmer than it was in the 80s and 90s. And by the end of this century, the average temperature is going to be more like 7 to 9 degrees Fahrenheit warmer. Very interestingly, these projections suggest that summertime in California is likely to warm faster than wintertime. I think this is important because here in California, we tend to be more heat stressed than cold stressed. And so if the warmest season is warming the most rapidly, then that warming is likely to have the most important impacts. By the end of this century, we're looking at a multi-model average of about 10 degrees Fahrenheit warmer than the 1980s and 90s. And so if you grew up in the 80s and 90s and your town on average reached a temperature of about 90 degrees during the summertime, then by the end of this century, kids growing up in the 2080s and 90s, they'll be experiencing averages around 100 in that same town, according to these climate models. Very importantly, the state will not be warming at the same pace everywhere. This is already clear, and it makes logical sense. The ocean is a great air conditioner. The Pacific Ocean will moderate the rate of warming near the ocean, and the rate of warming will be much faster inland. This has very important equity implications, as the coast of California, largely because of the air conditioning effect of the ocean, costs a lot more to live in on average. And so the people who are occupying the area near the coast very likely have the financial resources to weather the problems that come about from climate change more easily than many people in society. And yet it's the areas near the coast that are likely to experience the least amount of climate change, at least from a temperature perspective. Comparing nighttime warming to daytime warming, we see some interesting things. On average, they're both expected to warm about the same amount, but if we look spatially, we see lots of heterogeneity. In the areas in blue here are areas where temperatures at nighttime are actually projected to warm faster than temperatures during the daytime. That might seem like good news to you, given that the highest temperatures are during the day, and we may not want the extreme daily highs to get too much higher. But from an energy perspective, this might not play out all that well as solar energy production becomes cheaper and more widespread. Then the energy grid can more easily accommodate increase air conditioning demand or increase energy demand during the daytime. But at nighttime, we're still pretty heavily reliant on fossil fuels, largely natural gas. And so until battery storage is able to really advance and proliferate widely, then nighttime warming and increases in nighttime energy demand could end up having bad implications for California's desire to wean itself off of fossil fuel usage. How about heat wave amplification? Here we're looking at a map showing whether or not the warmest day of each summer is projected to warm faster than the average day of each summer. So red means the heat waves warm faster than average summer days. Blues means that it's not, and so you can that they're not, and so you can say it's a mixed bag. But many areas where we often see wildfire risks, such as the North Coast Range and northern Sierra Nevada and mountains around Southern California, are projected to actually have the hottest temperatures of each summer warm faster than the average temperature of each summer. If this plays out, then living systems that are highly sensitive to temperatures beyond some extreme high threshold may be particularly vulnerable. From a precipitation perspective, as Daniel suggested, trends in precipitation are highly uncertain. The average climate model projects just a slight amount of increase in precipitation if we average across the entire state, but you can see there's some spatial heterogeneity across the state of California. But very importantly, the precipitation projections are highly uncertain. Here now I'm just showing you the projected change in precipitation from each of 14 different climate models. You can see that there's a tendency for increases in precipitation, but they're really all over the place. The dots on these map indicate places where not even 2/3 of the climate models agree on whether or not, or on the sign of the future change in precipitation. Even though models are really uncertain about the magnitude of precipitation change in California, they are in greater agreement on how the seasonality precipitation is going to change. Models generally agree that precipitation totals in California will increase in the middle of winter, and in the rest of the year, not so much. In spring and fall, precipitation totals are actually projected to decrease. And what this means is a shorter precipitation season, which very likely, or which would imply an earlier start to the drought season. And in California, the drought season is already long, very high fire prone. And so an earlier start to the dry season translates to an earlier start, very likely, to the fire season. Importantly, even though there is great uncertainty about the future of precipitation totals in California, the precipitation or the future of snowpack seems much more certain, unfortunately. Because of warming, models consistently project dramatic declines in snowpack anywhere in California where snow regularly accumulates. In the Sierra Nevada, models on average are projecting a 50% reduction in the amount of water contained in snowpack, and increases in temperature combined with loss of snowpack translates to drier soils during the summertime. Again, even though we have uncertainty about what's going to happen to precipitation in the future, from a soil moisture perspective, models are fairly certain that the future soils in the heavily vegetated parts of California will continue on average to grow drier. This is because of the atmospheric sponginess effects that Daniel talked about. A warmer atmosphere is a thirstier atmosphere, and so precipitation doesn't increase, then that means ecosystems are left with less water. At the same time, we have snowpacks melting earlier, not forming at all, meaning the mountains begin losing their water supply earlier in the warm season. And therefore, as you get further and further into summer, then soils get drier and drier. This has very important and concerning implications for ecosystems, and we're already seeing these playing out. A drier ecosystem is a more flammable one as long as fuels are not a limiting factor. And so in California, we've seen something like a 10-fold increase in the annual acreage burned in forests and over the last 40 years. And the reason is because, or a large, very important reason appears to be warming and drying of the atmosphere. In order for if these projections of future warming and drying do play out, then a tree in the Sierra Nevada, in order to be able to continue to experience the same moisture conditions that it experienced in the 1980s and 90s on average, would have to move thousands of feet uphill or hundreds of kilometers north. Even though California's drought risk is increasing, as Daniel mentioned, so is the increase in, very likely, the risk of very intense precipitation will increase as well. Daniel mentioned that we haven't seen this yet play out in the real world, but the theory is a pretty simple one, straightforward one, that a warmer atmosphere can pull more water out of off of the oceans, and therefore, when a storm converges on California, the strongest storms should have more water to be wrung out. On average, by the end of the century, we expect the wettest day of the year to be about 20% wetter than it was in the late 1900s. And finally, just one note about what we think we know about the future of fire weather in the fall. In the fall in coastal California, that's where we tend to see our most catastrophic, fast-moving fires. Importantly, these fires are quite complicated. They require offshore wind events like Santa Ana wind events, and we don't know how those are going to change in the future. Theory says that if anything, we might expect those to weaken, which could be good news from the perspective of not wanting increases in bad fire danger. At the same time, the onset of the rainy season is projected to become delayed. We get these fall fires when the onset of the rainy season has not occurred before the beginning of the Santa Ana season, which also starts in fall. And so whether or not a reduction in Santa Ana windiness offsets the effects of delayed fall precipitation is yet to be seen. Another huge uncertainty is the future of vegetation itself. In much of Southern California, vegetation is often a limiting factor for the spread of fire. This year, now we've just followed 2 wet winters, there's a whole bunch of vegetation to grow, and so fire risk could be very high if we don't get the onset of the winter rains before Santa Ana's show up. The future of vegetation in Southern California is uncertain, and overall, we need to do a whole lot more work in order to understand how future climate trends and vegetation trends and human behavior trends will affect the future of fall fire in coastal California. Finally, I'd just like to remind you all that in this talk, I focused specifically on one pretty bad climate change scenario, one where we assume that we continue to burn fossil fuels at an increasing rate throughout the rest of this century. That is not the way that it needs to go. It is entirely likely that global society gets together and decides to curb greenhouse gas emissions, or that the market makes that an inevitability, in which case we will not experience climate change trends as severe as the ones that I've talked about in this talk. And so that's really a global issue and a national issue. But locally, there's more that can be done, even if we continue to burn greenhouse gases at a breakneck pace. Locally, there are management implications for how we adapt or handle the changes in climate that are to come. Can we have our water management practices change or be able to adapt to increasing noisiness from year to year climate variability, and not only growing drought severity risk, but also growing risk of floods, for example. And so with that, I will conclude, and we will segue into the final talk by our state climatologist, Mike Anderson.
Thanks, Mark. Hey, everybody. Be with you this afternoon. Let's fire it up and hit go. We'll start talking about state of California and what we're doing as we get ready for a warmer, wilder future. So first off, let's talk about seasonal water management the way it was. Wait for those fall rains to offset summer dryness. We just started water year 25 on October 1. On average, fall rains start up far northern part of the state on October 1. It takes all the way to Halloween to get down to San Diego for those fall rains to start. But we love having them start on time, because if they don't, then those soils are dry, particularly as the days get shorter, higher elevations get colder, and if snow builds on dry soils, 100% snowpack is not 100% spring runoff. We get into the winter. We look to mitigate winter flooding, restore spent storage, and then wait for that snow melt in spring, become the foundation of summer surface water supply. Then we rely on storage, supporting those flows in the fall until those fall rains return. Worked well for decades, but let's start to see why it's not working quite the same as we've been navigating these past few years. Narrative of climate change, well detailed by my two colleagues there. This is a graphic we developed back in 2005 to kind of set the stage on what we are going to aim to deal with. Well, let's look at it in the progression of change. We'll use statewide minimum temperatures for a water year. To look at this back in the early 30s, in that period of extreme that Glen was talking about, we had one of the warmest low temperature in years for the year in decades on either side, once in a lifetime experience. Get to 1980, it happens again. Okay, once in a lifetime experience. Hold your horses. Not so fast, because all of a sudden it's happening in the 90s, and not just once in the 90s, but a couple times. It's becoming episodic. So we went from an one-time extreme to something that's episodic. Now, if you look at the last decade, every single year has been warmer than that year that was extreme. It's now commonplace. In fact, it is part of our climate normal. Normal is defined by NOAA as a 30-year average, with which we operate in terms of deciding what's an average temperature and what's extreme. Well, let's look at the progression of that from the 20th century to now. Back at the beginning of the 20th century, 1901 to 1930, we see the blue dots. There are the 30 years that make up that average. And see that blue triangle, and the dot circles are close to that triangle, meaning that the average, represented by the triangle, fairly representative of each individual year. Fast forward to the current climate normal, 1991 to 2020. You see in the table, we've warmed 2 degrees Fahrenheit. So also see that with the shift of that large diamond being to the right of that blue triangle. Now we see average precip-wise about the same. But if we look at the individual years, they're nothing alike. Orange squares are scattered all over the graph with new extremes. And if we look at using the average value as a predictor, we're finding none of the individual years come close to that. So average not as great to use as a predictor. No, why is that a problem? But we look at it and we say, well, okay, we build a water management system under an expected set of outcomes. And here we're taking all the years and we're just putting them into their percentile, where they lie in the distribution. And we look at the last decade, and I use this graphic with water managers and say, if the last decade's been hard for you, here's why. Only 1 year in the last 10, from 2013 to 2022, and we'll talk about the last 2 here in a second, fell in that expected range, meaning everything works as designed. We get into the anomalous space, have to make some adjustments, but should be able to manage. It's once we get into the extremes that we really need to do things like emergency orders and really operating in an extreme emergency environment. Unfortunately, we've been there a lot, and it becomes challenging because those methods that you use during extremes should only be used once in a while. They're not designed to be used every year. In 23, we added this, and talk about that dry to wet shift. We went from continuing that 3-year drought that Glen talked about. We were at Christmas and well into what was looking like a 4th year of drought. Again, in record-setting territory with record lows in some of our big reservoirs. Just after Christmas, 3 weeks happened and we had winter, essentially. 46% of our annual precip showed up in that 3-week period, 86% of a seasonal snowpack. Many floods a record, but that wasn't it. After a month off, we had cold extremes that put snow in many places that aren't used to snow, didn't have snow removal equipment. Creates its own new type of extreme. Weren't done there yet, because then we followed with more atmospheric rivers, creating peak flows in the Tulare Lake bed that did cause the Tulare Lake to return. But to give you an example, the smallest tributary downstream of Pine Flat Dam on the Kings River, called Mill Creek, you walk across in the summertime because there's no water in it. During one of these atmospheric rivers in March of 23, it had a peak flow of 11,000 cubic feet per second. The Kings River channel downstream of that confluence with that creek is only 9,000 feet per second. So these are the scale of extremes now we're starting to see and have to figure out how we deal with. So let's look at it. If we're not going to do things seasonally, let's talk about building a water year. And on the bottom side, you see kind of what a water year expectations are. Fall rains start in the fall. Half our annual precip shows up in December, January, February, 90-day window to get half our annual precip. March, that great transition month, sometimes referred to as the March miracle. If winter fails us, maybe March bails us out. April 1, historic average peak of snowpack, peak melt in the northern Sierra, late April. Early May for the southern Sierra, higher elevation. You see there in 23, we were very late because we had such massive snowpack. And you see some of the statistics there on the top. Water demand peaks in the summertime as it's hot and dry. So we need to take the water in the winter and hold it over for the summer. Snowmelt makes a great vehicle to do that. As you heard, though, it's going away. So we're going to have to find a way to mimic that. We have heat events. We have tropical activity now. August and September, the winds in the middle latitudes tend to weaken. And when they do, those tropical systems, either forming in the Eastern Pacific or occasionally in the Western Pacific, are allowed to wander north. Now, as it gets further north, if you're on the west side of the Pacific, you can get into that jet stream, kind of zipping across the Pacific. And those tend to influence more Northern California. Those coming up in the Eastern Pacific, like Kay and Hillary, tend to impact Southern California more. By then, we aim to get to the end of September and have some end of season targets and figure out, all right, how are we going to get into the next year? But looking at it on a yearly basis, we need more detail, right? So here is water year 2022 with statewide maximum and minimum temperatures. The dashed lines for climatology. The solid line is what transpired each day. If you see it colored in a space, that means it was in the top 10% or bottom 10% of the distribution. The dots mean it's in the top or bottom 1%. So we see that Labor Day heat wave back in September when it got up to 113 here in Sacramento, 116 in Healdsburg on the Russian River. Record temperatures that were definitely not comfortable at all, and both daytime and nighttime temperatures are hitting there. But in one of the hottest years in history, we had a cold snap in May that may have caused agricultural damage. How do you claim damages from cold in one of the hottest years on record? The way you do it is if you have the right data that can tell the story. And finding a way to characterize and tell the story, and this brought to us by the Center for Western Weather and Water Extremes by Kristen Gerges at Scripps Institution of Oceanography. One way to start doing that. We have this from our colleagues at CW3E, Chad Hecht. Builds these every year. Gives us a look at what happened for the year in terms of atmospheric rivers, where they make landfall, how big, how strong they are. And this is great because we have a physical mechanism to study that relates to the key drivers of water arrival in the state, as well as our flood risk. And in this case, this is a drought year. 61 atmospheric rivers made landfall on the West Coast, but you see most of them hit Oregon and Washington, really focusing on the mouth of the Columbia River. However, that is the exceptional AR in October that went right through the Golden Gate, which was absolutely fabulous because water year 21, the previous water year, was the second driest on record. And that then 20 and 21 became the driest 2-year stretch on record. This thought, boy, we're off to a great start. It's going to be great. Unfortunately, everything turned off at Christmas, and we end up with a drier than average year with a record-setting dry start to the calendar year. So finding ways to characterize our environment, like I've shown you here, are one of the key ways that we get better at adapting. But, so I know more about atmospheric rivers, but what I need is a climatology of them. So our friends at Scripps put online the coastal landfalling atmospheric river catalog, giving us counts by years back to the 1950, how big they are as well, showing the size of the atmospheric river. And then also showing the angle at which they're impacting us, because this is important. The amount of water vapor moving over the ocean, coming high speed, entering California, it's in the lowest part of the atmosphere. That means it's going to interact with the topography. The angle it impacts the topography depends how much rainfall falls out where. And so this is one way, again, to characterize it and give a sense of how weird have things been. All right, how do I take all that information and do something with it? Well, here we go. We're going to switch from seasonal water management to real-time water management. We're going to increase our managed volume capability, meaning with each storm, we're going to work to maximize the benefit and minimize the hazard out of the water that comes down. And how do we do that? Well, we want to work on improving our observations, Also forecasts longer lead time, more choices, more opportunities to position the resource in a productive space. But I can have the coolest observations, and I have some really cool ones, some great forecasts, but if I can't turn it into what to do with that information, it doesn't help. And that's why decision support there really forms that base that lifts the triangle, lifts the managed volume capability. And in this, we really know about precip, but we really have to understand how temperature fits in the picture. My colleagues did a great job of articulating that. I put at the heart of it, really understanding atmospheric river research and associated research more broadly across the landscape is going to be key to making this a reality. There's also 3 key elements that need to happen. It's communication, collaboration, and coordination. You have to work together if we're going to make it through. We've got a good basis to set that up. So how do we do it? Well, Water Year 23, here's an example of how we did a lot of this because we had in the midst of all that flooding, still drought impacts in the same county. So what do? Well, one, we have some really cool partnerships with the NOAA and the Air Force, and they are now running atmospheric river recon. Folks on the East Coast get hurricane hunters flying into hurricanes to get better data on them, get better forecasts. We now have them doing it with atmospheric rivers. That program has improved weather forecasting as much as all the balloon launches from airports across the United States. Great program started here in California and benefiting the nation, but significant benefit to California. We found out that using indexes to tell us how much snow is there and how much water is coming off doesn't work so well anymore. Actually, a spectacular bust in 2021, given those dry soils and a record dry and warm spring. So we have a program we've been working with NASA on new technology to actually map the snowpack. So we now know where the snow is distributed on the mountain. This is really important because those higher elevations, it can still snow, but as warmer, it holds more water, meaning the snow gets deeper, higher up on the watershed in some places. Being able to map it, understand the snowpack better, we can better predict its melt, its flow into our reservoirs that we manage, and manage not only just water in the surface reservoir, but managing surface reservoirs, coordinating that with what we do with our groundwater basins. Taking, again, a lot of communication, collaboration, and coordination across agencies to make sure this all works and aligning federal, state, and local interests. Through those coordinated operations with reservoirs, we now manage the downstream condition, minimizing flooding where we can, maybe doing some managed aquifer recharge where we can, and getting down to the coast. And then really understanding how the rivers and sea come together and create potential hazard at the coast and being able to better describe it, enabling better planning to happen with our coastal communities. All right, something for you all to watch if you want to follow along with us this year. We have the California Water Watch. As you can see across the top there, precipitation, snowpack, reservoirs, groundwater temperature, stream flow, soil moisture, and vegetation. Really trying to get better at that spatial information. The website's there. Really working to continue to improve this, develop some products with our colleagues, with NASA and some of our other agency friends, and even some public-private partnerships to develop content for this to better inform state of the watershed, and then with our forecast, what's coming next. So now when we look to build a water year, this is what we have to think about. Fall, those fall rain, when does precip onset happen? What's the temperature anomaly? How dry is the soil when the snowpack starts building? Because we get into the big 3, December, January, February. It's really not wet or dry, it's wet and dry. Really understanding the timing, pace, and scale of those storms and being able to have enough time to manage them to the best beneficial use of the water, minimizing hazard. Really being able to predict those notable anomalies, enabling the right adaptation to happen because it's not flood or drought, it is flood and drought at the same time. In spring, we look for that late season bailout or potentially the early shutoff. We've seen the early shutoff both in 2013 and in 2022. Again, an extreme that has become episodic. Getting better at it is in our best interest. Really understanding when we're going to get peak snowpack, the timing and magnitude, and because of that soil moisture knowledge, knowing whether 100% snowpack equals 100% runoff, or if we have a tax to pay and less water available as we get into summer. But as Park detailed, it's really understanding the drying pace and scale as well, how quickly we dry out, and that transition of how the vegetation consumes the available water for themselves before they move into stress, senescence, or in the case of some of the larger vegetation, the trees, there's just not enough water to keep them alive. The heat events, we've all experienced them this year, and certainly the one that's ongoing and likely to last another 10 days. Tropical activity, really seeing some new things there, and I will point to Hurricane Helene on the East Coast, going from a tropical depression to a Category 4 hurricane in a matter of 2 days. Change that quickly challenges the ability to plan an appropriate response. So really understanding the physics of what's going on and what's possible, not what we're used to, is really important. Another thing for California, it'd be great to know, yeah, it's a dry year, but even better yet is the start of one dry year, another multi-year drought. Really working with the research community to see, is there anything at all that can be said in that arena? And then really finally understanding the bottom line here. How much different will this next decade be than the one before it? Because 2011 to 2020, very different from the decade it replaced, 81 to 1990. And that is expected to continue. And the way we understand then how to use the climate normal and how it relates to what we're doing will be beneficial if we understand that. All righty, that wraps things up for me. I appreciate your time. Just a nice graphic of that October 21 storm where we had record low pressure off of Aberdeen, Washington. But as you see, the atmospheric river all the way down at the Golden Gate, bringing in record-setting precipitation for many parts of Northern California. All right, thanks. Now, Glenn, back to you.
Well, I want to thank our speakers for giving these really detailed and in-depth analysis of where we are and where we're headed. I think this is very, very important, and I thank you very much for spending your time to do that. I also want to thank our audience for bearing with us through some of the fits and bursts we had with the IT. This is recorded. We will be making it available. We would like you to share it with other people. We would very much like you to share it with other people. So I want to thank our audience, and I want to thank Hollis Lenderking for endowing the chair and allowing us to put on these Ursus symposia for you. I know we're over time, but we had questions that came in, and I would like to then just take a minute, and I would like very short answers from our panel. To answer where I put together a couple of the questions some of the questions that have come into sort of overarching ones. And one of the questions was this: will the things that we see happening, are they going to affect underrepresented, communities of color, communities which have less socioeconomic clout in a sense? How differential are the effects that we're seeing? Will they become worse in the future? And what can the state do to try to level the playing field so that we have some environmental justice in the way that we handle these challenges? And so I would invite anyone to pop in quickly. And again, I've agglomerated some questions with very, very brief response to that.
Well, I can jump in for a moment, and I think the video is turned off, so I'm not sure I can share my screen. But
yeah, just words, no more PowerPoints.
Yeah, I mean, I think that one of the things that we saw in Park's presentation, and this has been kind of a theme in a lot of the work that's been done on extreme heat risk in California, is that unfortunately, this existing temperature differential where the coast is cooler than inland areas and has more manageable temperature extremes is likely to become even more amplified in a warming climate. And because that is in almost the exact opposite direction as the wealth and a gradient in California, in other words, it's more expensive to live on the beach as you'd expect than it is to live somewhere inland where it's a lot hotter. This is true both in the San Francisco Bay Area, it's true in the LA metro, it's even true in San Diego, and even, on a statewide basis, this is even true like Bay Area versus Central Valley kind of dynamic, or LA County versus Inland Empire. That is going to be a big challenge because we know the impacts of extreme heat are very high. So we know that the climate is changing specifically against the gradient that makes that potential extreme heat inequity worse. And also we know that a lot of the places, even within a given city, it is the poorer neighborhoods that have less urban tree canopy, less access to active cooling. I mean, air conditioning is in many ways kind of I know some folks don't like it because it uses a lot of electricity, but the reality is if you live in a really hot place, it is the only way you're going to be able to, safely sleep at night in some cases. And so, I mean, the good news about that is that the active cooling part, that's something that can be addressed through policy. The street tree kind of challenge where the poorest neighborhoods have the least amount of passive cooling, that is also something that can be addressed through policy. Now, we can't reverse the temperature gradient, either the climatological one or the ones that's changing in a warming climate. But I think, that's a classic example of where there probably is going to be a pretty clearly differential impact all, in very different parts of California. And yet those impacts are not inevitable because most of the negative harm that comes on one end of the spectrum is mitigatable through a number of different kinds of interventions that you could take.
Okay, great. Thank you. Park, do you have anything quickly to add to that, or should we go to the next question?
No, the thing that comes to mind is wildfire and wildfire risk, and not knowing how that's going to really play out in terms of equity. But right now across California, many people are being impacted by insurance companies being hesitant or terrified of insuring California because of their uncertainty about what's going to happen with fire in the future. And so people, fairly or not, are being excluded from insurance very quickly in a way that's a surprise. And so the state, I believe, is going to have a lot of thinking to do about how to handle that. What is going to happen to settlements that become uninsured or uninsurable? And are there ways, are there scientific advancements that can be made in order to give insurers more confidence in their ability to predict future fire risks?
Okay, great. Thank you. I'm going to ask then, and this will just be our last question because we are over time, but this came up in social media and it came up in our Q&A here. And the Q&A here was, well, aren't you guys just preaching to the choir? And on social media, we had quite a few people saying, well, this is just made up, and why are the states spending money on this? Why are the universities spending money and time on these issues of climate and climate change? And so my question is then, I think that we are all convinced by the evidence, by the hard facts, by what we see on our thermometers. If you hang one on your wall and look at it day after day, year after year, that something is going on and that the direction it is going is going to be problematic. So I'm wondering how we can better communicate in a way that reaches people and convinces people that, well, this is something that we do have to take seriously and it is worth our time to spend our careers in. So you're both excellent communicators. I would very brief kind of response. Yes, what do we do better to get the word out? Because there are still people who are skeptical about the amount of time and energy that we spend on this. So I'll go ahead and start with Daniel, and then I'll go to Park. And again, we have to, in the sake of brevity, encapsulate your answer, please.
Yeah, I mean, I think briefly, there are two pieces to this. I mean, and one is, in terms of preaching to the choir, I mean, I think one of the themes you saw in all of the three presentations today is that while there's fairly high certainty about the big picture, there is actually still quite a bit to figure out about the details. And as some of the comments that we're not having time to respond to directly have reflected, it is those details that actually matter pretty dramatically on the ground in terms of actually doing things to prevent potential harm or improve outcomes. And so I think even, in the context of preaching to the choir, I mean, I think even among climate scientists who focus on California, there is actually some, range of opinion on things like precipitation extremes, for example, or wildfires. And so I think the big picture is clear, but it's actually the details that matter, I think, that we are still working through. And, just as an example, frankly, I think the state of California and many individuals within the state were for many years planning for a future that looked perpetually drier, less precipitation, hotter all the time. It is hotter than it used to be. It will continue to get hotter, and we are going to see worse droughts. In fact, we already are. However, we're also going to see these really wet periods, and that results in a different set of potential actions than if we were continuing to make the assumption perhaps that was made 10 or 15 years ago. So maybe I'll just leave it at that as my piece.
Mark?
Yeah, I'm not sure. Some people are going to think that that if we communicate about our climate research, then we're preaching to the choir. Others will immediately write us off as not being right or motivated by something other than scientific purity. But in the end, I am just motivated by a pure fascination with the Earth's climate system, and so far that that fascination has, I think, kind of translated to pretty influential work and communication. And it's even though it's serious business, it is just super interesting and very fun for me. And so that's I'm happy to just keep being a scientist and not worrying too much about people's interpretations.
Okay, I want to thank you both. I do want to say to our audience, we have a lot of really good questions. Some of them were directed at policy, and they would be most appropriate for Michael Anderson, but he had to leave for another meeting. There were questions about water resources or the allocation of resources to disadvantaged communities or smaller cities. We will keep all of these questions. We will pass them along appropriately. Unfortunately, Michael could not stay to answer them, but we really do appreciate your questions and what you've asked. Again, on behalf of UCLA and the Geography of California and the Western United States Endowed Chair, I want to thank you for your patience. I want to thank you for joining us, and please keep your eyes and ears open for our next Ursus Symposium. Thank you to our speakers, and good afternoon to everyone.